brings that light to a focus, and that focus is happening here on the back surface. It's called the retina. There's a medium in between. This is called the Vitreous Humor. That's a clear jelly-like substance, and it's designed to help maintain the pressure inside the eyeball because it's kind of a fragile organ when you think about it. But all it does is maintains the shape, and the shape is very important because for geometric optics, in order to get the light to form an image properly on that surface in the back, you have to maintain the shape and orientation of the components very carefully. So most of the eye is this empty space. It's just filled with this gel, but it's this lining of cells on the back side of the eye that's important, and they've blown up a little section of it there to show the cells that are in this very, very thin lining on the back of the eye. And the important thing to know is that there are two main ways of forming images, although you have more types of cells than that. So if I look in a little bit closer on that, so now I'm just talking about that fraction of a millimeter thickness of the retina. Those two kinds of image forming cells help your eye work in different levels of lighting. You may have heard this before at some point. You have things called rods and you have things called cones. And they are kind of intermingled here at the top level of this layer of cells that's in the retina. And you'll notice that these things that it's pointing to that say cones have different colors. They're not really those colors. That's rather intended to tell you what kind of light they sense. We have color vision, which has turned out to be really useful for us as humans. It's helped us get along in the world. Being able to discriminate colors is part of what's helped us to survive. To do that, we have what's called Rgb Vision, red, green, and blue. And all the other colors that we sense are made up of those sort of primary elements. So we have light sensing cells in the retina that are more or less sensitive to those three colors specifically. And depending on how many photons of light come in and stimulate those receptors that have response to those particular colors, the message that gets sent to the brain is, this is a blue object, this is a yellow object. This is a white object because it reflects all the colors of light coming from it. This is black because it's not reflecting any light at all. So this turns out to be really great if you're in a high light intensity environment. But as you start to bring the light down, these cells are no longer very good at what they do. They need a lot of light in order to tell you something about color. So in order to get around at night, because humans we're mainly what they call diurnal creatures. We mostly do our business in the day, but we need to be able to get around well enough at night to make sure that we're not eaten by a lion out on the savannah or wherever we are. So we and other higher animals developed a separate set of cells that are called rods. And they're so named for their apparent shape, just like the cones were named for their apparent cone shape. The rods are really good at detecting low light. But they don't tell you a lot about what you're seeing around you. They just kind of give you a sense of intensity. So they're good at low light levels, but they don't give us good discrimination of color. They don't give us good spatial discrimination. And where they're at in the structure of the eye really depends on how good your vision is in any particular direction. I will also point out there is, and we have only discovered this in the last 20 years, there is another set of cells in the eye that's not image forming, but it tells us what time of day it is. They're called intrinsically photosensitive retinal ganglion cells. It's not going to be on the test, by the way. But these are kind of sparsely scattered around the retina, and the discoverers of these cells have described them as twilight detectors. What wakes you up in the morning if you're out camping? The sun, the sky getting bright in the morning. The sky is really blue in twilight, right? Then the sun comes up and the colors start to shift. But during twilight, your eyes are flooded with intense blue light. These cells detect that blue light. They send a signal to the brain that it's time to wake up. And without that tying in your circadian rhythm, this daily 24-hour cycle, to the rising and setting of the sun, you quickly become unmoored from the length of the day and the length of the seasons. So we need these in order to sleep properly, know when to wake up, etc. And again, we're still discovering things. We didn't even know about this a few years ago. This is the only slide that might be a problem for the squeamish, but I thought this was important to point out what the back of the eye looks like. This is an image of a retina in a human eye taken by pointing a camera and a light into somebody's eyeball, who was very patient with the whole process. And what I want to point out is, if you go back a couple slides here, you'll notice that there's this stalk hanging off the back of the eyeball. And all of the signals that are being generated when light strikes these cells, they're sending signals to this back lining surface of the eye. All those electrical signals are then being channeled into this thing called the optic nerve. And we can see that if we look into the eye. This is the footprint of the optic nerve on the back of the eye. That's a blind spot. There aren't any receptors there. And there are some neat tricks that you can do that will show where your blind spot is. Because we have stereo vision, so we have two spatial channels, that kind of covers up the fact that there's this blind spot there. We don't notice it unless you trick the eye into showing you where it's located. But what I also wanted to point out is, separately from that, in another part of the retina, there's this area called the fovea. You probably have noticed that when you're looking straight on at something, like think of faces of people. You're in a crowd, you're talking to one person, you're looking right at that person. You really know the details of the face of the person that you're talking to. But if I'm talking to one person, I have no idea what these people look like. And that's no accident. Our what they call our visual acuity, our ability to form detailed images, is for good reason straight ahead. That's the largest density of these light-sensitive cells, these cones, is in the fovea. Right? So already we're talking about a pretty narrow field of view in which you have a detailed view of the world. Everything else is in the periphery. And you don't have as good a visual acuity out there. We have to take this into account when we're talking about lighting spaces at night. People are really good looking ahead, not so good looking off to the side. Then we're going to couple this with the fact that the cells are really strong here in terms of their density, and they quickly fall off when you move away from that. So we have to treat the peripheral areas. Think if you're looking at a pathway, for example. You don't want people to fall off the path. But when you're walking down a path at night, you're kind of looking at the edges, but mainly you're looking out straight in front of you because that's the direction that you're walking. The point is, if we take into account these anatomical aspects of the eye, it helps us do better in planning how we're going to do the lighting.
You could point out that the fovea is also the highest concentration of cones. There's not a lot of rods in the fovea. So that accounts for the thing of averted vision. If you're looking at a faint star, if you look right at it, you really can't see it too well. If you look just off to the side, you'll be activating rods instead of the cones that are at that fovea.
So if I took this picture here, and I drew a line across it, and I asked, as I move across that line, what's the density of those different kinds of cells? So what Pete is saying is, here's the fovea basically. This plot, the green tells you the density of those cone cells, and it's really high when you're right on the axis of the fovea. When you move off it, the numbers fall very quickly. Whereas the number of rod cells is rising as you move away from the fovea. It picks up quickly and then slowly trails off. So that's the effect of this averted vision. If you're in a dark environment and you're trying to see something that's very faint, if you move just slightly off axis one direction or another, you start putting that faint light on the things that are really good at detecting faint light, and all of a sudden you can see it. So again, this contributes to design because it tells us something about how we expect the eye to work under different circumstances and what it's able to sense most efficiently when we're looking off the main axis. So what this results in is there are three fundamental types of vision. There's a bright light version that really relies on the cones. We're going to have to do a little jargon here. This is called photopic vision. You have its counterpart over on the other side that deals with very low light levels. That's called scotopic vision. These are all Greek words. Skotos in Greek means dark, photos in Greek means light. And then there's this third kind of vision that we're still kind of getting a handle on exactly what it is, but it's this intermediate state where, yeah, your rods are doing their thing, the cones are doing their thing, and you're sort of in this intermediate level of light. This is what we don't know a whole lot about. There haven't been a great deal of studies. We understand photopic vision really well, scotopic vision. This is still something of a new concept. But again, depending on the intensity of the light, you get these different performance characteristics of the eye, and therefore your design really has to account for that. But what this also says is, going from a very bright environment to a very dark environment abruptly, or vice versa, could be really problematic, right? You want to step people down between these high and low levels so that they're not suddenly blinded because they walked from a dark parking lot into a bright interior, or the other way around. They're in a brightly lit interior and are adapted to that level of light, and suddenly you send them out into the darkness. You want to step them down in an appropriate way that preserves safety, so that they can see, taking into account these different ways that the eye works. And then somewhat related to this is a phenomenon that if you spend some time outdoors around sunset, you'll have noticed. It's called the Purkinje effect. And this is what is happening is we're transitioning from that photopic, high-intensity, cone cell-driven type of vision to this low-intensity, rod cell-driven type of vision. And part of what happens is our sensitivity to different colors of light changes as we adapt down through those different levels. And it shifts more towards the blue end of the spectrum. That's going to have a really big implication when we start talking about LED lighting. So that means that the reddest colors are the first ones to go. So the series of images is meant to show what happens under daytime lighting conditions, and then as you go into dusk after sunset, the reds are the ones that disappear first. So the greens and the blues are still fairly discernible, but by the time you get to darkness, you really don't have any color distinction at all when you're out in the field. So this has some implications for how we do lighting in terms of the color quality of the light at different lighting levels in terms of what we can actually sense. So what happens if I shine a bunch of light in your face? Number one, you probably don't like it, especially if you were just in a dark space and then I come up in your face with a flashlight. But the eye responds. Our eyes are really good in many respects. They're active over a large, we call dynamic range. They can give us usable images and information. But if you cause them to move between these different kinds of vision abruptly without an opportunity to adapt to them, you have some problems that are associated with that. And on a mild level, it's just a sense of discomfort or pain associated with the eye trying to rapidly adjust to a bright light level as we're shining light directly into it. But there are also these other aspects about the changing depth of field of the focus of the eye and the reaction time changing. So think about coming around a corner. Who hasn't done this? You're out in the country somewhere and somebody comes around a corner with their high beams on, right? And momentarily, you don't see anything but those lights because your eyes are still adjusting to the situation and trying to figure out what to do. So mitigating glare turns out to be something that's important, and that comes back to how vision works. And then as people get older, their needs change. And that's because the physical anatomy of the eye starts to change. The lens of the eye begins to yellow due to years of ultraviolet light exposure. That changes the amount and wavelengths of light that are able to be transmitted through the eye back to the retina. And so you can get this effect, it's called veiling luminance. When you hear people talk about being night blind, they don't like to drive at night. Magnify that by about a factor of 1,000 if you have cataracts, because now there are bright halos around everything. And that again, it changes the contrast between the thing that you're trying to see in the background, and it can make it hard to see those obstacles. So when we do lighting design, and we're putting all of these new, very blue-rich white LEDs out there into the world, we're really disadvantaging older people. And if it takes away their ability to drive safely at night, you have impacted their quality of life. And it all ties together.
John, I'm a chemist and I worked in spectroscopy for some years. One of the things about cataracts is that the proteins in the lens actually start to crystallize. And before you have a cataract, you still have a certain amount of crystallization. And what that does is it scatters all the light that comes in, which is where the halo comes from. But that process, you don't have to have a cataract to have that process starting. At about age 35 or 40, that happens to virtually everybody. And so it's not just older people that we're looking at here, it's all of us from about 40 on up start to see that light scatter. It's only when you get big crystals you call them cataracts.
That's a fair point.
And something that's very salient to this particular function is that lighting testing that has been done with people. I know the Virginia Tech Center has a lot of work going on, and they exclude everybody that has cataracts, and they exclude everybody over the age of 45. Okay, so to say that it's a good sampling of the driving public, or the public who's outdoors and has to experience light, it's not at all valid as far as a statistical sample of the populace.
They exclude over 40, you said?
45.
45.
And particularly when you look on the bell curve, baby
That's,
boomers
I
jumping.
know. So what's
It's
the
baby
largest
boomers.
segment of the population that's growing is going to be people who are going to be more and more affected by the spectrum. And the veiling luminance, I'm 59, and it hit me at 54, okay? And, you know, it's just,
Did you say,
it's something else. And so if you're not there yet, it'll happen, but the experience is profound.
so what is the veiling luminance? Again,
It's when the
halo effect.
It's a combination of that and the vitreous humor itself doesn't become as transparent.
Okay.
Okay, you get the artifacts that are in there, and you can almost see like segments of it. It's a peculiar thing. When you look at a blue sky in a neutral background, you can actually see far more, other than the floaters, but distortions within the field of that fluid. And all of that comes into account when you get this light coming into your eyes.
So if we want to challenge a municipality's use of bright blue LEDs, we threaten an age discrimination class action. We talk about the age discrimination in their lighting.
I'm being very careful and being very silent about that. Draw your own conclusion.
And we also, I mean, I had the LASIK surgery years back, and that's where my halo started, and now I have cataracts. And so we got a huge chunk of the population who's had that LASIK surgery.
Yeah, I know.
Who gets the vein.
And I've had many say to me that the LED advent of that has really made the LASIK a regrettable decision.
Yeah,
Wow.
I did it for better observing through the telescope.
Oh.
And now I don't do it.
Oh.
So the bottom line here is understanding how our eyes work and how they talk to the brain, and all of this is something that can contribute to, in theory at least, coming up with some better lighting design that's more attentive to the needs of the people who will use the lights, rather than the convenience of either the people who design the lights or put them out there or have to pay for them. Okay, let's move on to some lighting technical concepts. Mostly leads to you, so take it away.
Just the notion of how light is measured and how we quantify it. You have luminance and illuminance. Illuminance, and that is the luminance. So the luminance can vary greatly depending upon the substrate. And there's all kinds of effects that happen because of this coefficient of reflectance that's associated with the substrate itself and how design should take place.
So the main point, this is probably the most technical thing that's in the whole presentation, is you're going to see these words and you're going to see people who are going to try to use them to confuse you. So we've tried to distill it down to something that's as easy as possible to understand that some of this is about the source and some of this is about what receives that light. So there's source terms and there's received terms.
Yeah. Shining off and reflecting off. Right? Shining
And then-
down on something and reflecting off of.
And the illuminance is a measurable lux.
Yes, I could put a detector down at this surface that would tell me how many lux of light are falling on that surface.
Okay.
But if I'm over at the eyeball and I'm looking at it from a distance, instead of the light directly falling on it, it's reflecting off of it, then I'm going to measure a luminance that has different units. That's what these things in parentheses are. They're units. It's a unit of the quantity of the measurement.
So the issue with luminance is partly because of the light itself. Maybe it's too many lumens for the job, but maybe it's what it's hitting. Maybe instead of being concrete, there should be more grass that might absorb it,
Or
planting.
reflected. And these things are well known. In fact, there are the species of turf grass has different luminance levels. And they'll take that into a calculation. Whether it has been mowed or not, the direction of which it has mowed will have a different reflective
Ha!
coefficient.
The
So
direction of the way
the
you mow.
age of asphalt, new asphalt versus old. Concrete, the types of materials that are within the concrete will vary the coefficient of reflectance. So we're talking, you're really getting into the weeds, here when you're talking about all the things that can affect light, its measurement, and its applications.
Literally figured.
Yeah.
This was a very helpful slide.
The shielding, the concepts that had been used in the past, really, and this is somewhat, they're abandoned terms, where you had no cutoff, semi-cutoff, cutoff, and full cutoff. And these were terms that, in my opinion, begat confusion. When you hear cutoff, that to me sounds like nothing's there. Well, what's full cutoff? Okay, so in the old days, semi-cutoff allowed 5% of the light to go upwards. Cutoff allowed 2.5% of the light to go upwards. So it sure looks like there'd be none, but no, 2.5 was allowed for cutoff. Full cutoff was none, but it actually had a limitation within the 80 to 90 degree as well. And these terms are no longer used. Imagine that. There's also terms that are ambiguous, and that is shielded versus fully shielded. What do those exactly mean? There's not a standard definition. It kind of has to be made up in a glossary, whatever document you're reading, whatever presentation you're hearing.
So you'll still see these terms
Oh,
in wide
yes.
circulation.
Yes.
Sure.
You'll hear them from
Yeah.
city council people and city engineers and lighting people, and this is what we want you to think about instead.
Right. Does it shine down or does it shine up? That's the importance. Keeping it down. The angle over here does come into effect. This is more, we consider the glare angle. Particularly with LEDs, it's just as a point source, it's going to be more glary to begin with. LEDs, luminaires in general, have more glare than an arc tube. It's just the notion of light coming out of a surface this big or light coming out of a surface that big. And that's, you got a chip and you got a little bit of a small surface area that's putting out a lot of light, it's going to be glary. Believe me, the lighting designers are aware of that. They're trying to come up with any way of diffusing, making it better, while still maintaining distribution types. And it's a challenge. They say, well, just put a diffuser over the whole thing, then you have one type of distribution, and not all the many that can be used to focus the lights as specifically as they want them.
What about some of the fixtures, because the new fixtures that we have, I mean, they call them shielded, but the LED lights actually true outside of, below the fixture. So the light is actually scattered this way.
There's some designs where it looks like it would be a
Yes,
full
there's
cutoff.
not a lip over it,
Right.
right? So it's not
You're right,
fully
so
shielded.
that's
So
why
it needs to be recessed up into this housing.
Right, so they
Yeah.
call these shielded,
Well.
but there are a lot of fixtures and ours
Yeah.
completely protrude and they
Yeah.
create.
In our
those
fixture
things.
shield approval program, I validate it by photometric performance. And looking at one, I cannot tell. It says, what does the gonio say? And if it's, no light shining, cases. Believe me, I turned down a lot of people who have submitted an application saying, of course it's fully shielded, look at it. All you have to do is tell. It says, no, all you have to do is look at the photometric report. And light is shining upwards, and I'm sorry we cannot approve this product. And so what do we do? It says, make a shield. Do whatever you can to make sure the light doesn't shine above that 90 degrees. And many go back to the drawing board and, yes, get registered with us. And others say, the hell with it. And that's the way it is in the lighting industry. Everyone?
The word sparkle is used in some of these parking lot lighting fixtures. They want a little bit of sparkle
Yeah.
to draw your eye in.
Yeah, and
A little bit
that's
of
also
drop.
one of the home and garden terms, that we hate. And the lighting industry has gone back and forth as, shall they define sparkle? And so far, they've chosen not to, which is fine with me, just yet another awful term.
So why do we shield lights?
Yeah, that's brilliant. Those trees are very safe now. And this is a closed facility. You cannot drive into the parking lot. And what's the point? The point is it's on a timer, and that's what Phil designed in 1962, and we just kind of left it that way. So
So this, we're well designed you wouldn't really be able to see anything above that red line because the light would be confined to the space below that horizontal plane.
And if it were really well designed, it'd be lighted, so all you're doing is lighting the
Exactly.
surface that needed. And if it were really well designed, it'd be
be
off.
But if it has to be on,
Yes.
he was talking about this notion of a glare zone. They used to try to deal with this by this full cutoff terminology that was intended to keep light down below that horizontal. So there's that horizontal line. And ideally, you would do it this way so that the light was only on the target surface where it was needed. It didn't run across the property line and trespass onto the neighboring property. But it's important to note that light that comes down in these first few degrees is really damaging in terms of the glare impact. So if you're talking about, I'm putting a lighting installation here, this is great, it keeps the light on the property where it's intended. But if I'm not careful about controlling the light in that so-called glare zone, I'm creating a problem for somebody who lives a mile away. They're nowhere near the source of the light. But that could be enough glare to create a public safety hazard, for example. So this concept of glare is extremely important. If you're experiencing the phenomenon of glare, you are dealing with essentially wasted light. That light's coming directly into your eyeball. It is not helping you see a thing.
It's often incorporated into design parameters of a fixture to give better uniformity. They're trying to light out there from over here. I have seen, just kind of as a generality, retrofitting a luminaire onto existing pole structures usually have more glare than an installation that was designed from the get-go with the poles spacing taking into account the design of the luminaire. They're trying to achieve more with a product by putting a heck of a lot more light up here so they can squirt that light out better because of the existing pole spacing. In new pole spacing, you don't tend to see that. Yes.
I just, that light beam coming down, is there a degree of angle that should
Here,
be
here,
less?
here.
No, the actual light beam.
So here.
Yeah, here.
It would depend, I think, on the design, which you were attempting to light. But this is the kind of control that a lighting designer can exert through good design, right? Especially now, and it's one of the nice things I'll say about LED is that it gives us incredible control. You can have this come right up to the edge of that sidewalk and not spill over it at all. But back to that slide about mindfulness plus technology equals solution, you have to be thinking about it and then go to the technology that enables it. So yes, you could have there's no magic number here about this particular angle. The point is that the light is confined just to the region that needs to be lit, and the design has accommodated that.
And a good designer will take that into account, knowing that there's going to be different configurations desired and available to the installation. If you go to a place that say, we want to have the lights only go to the sidewalk, okay, well, they can do that by putting proper shield, the proper, or there may be a neighborhood where the policy is they want to light up to the keyhole where they walk in, okay, that's what the community wants, okay, and if you take that into account, it can be done. But if you take a one-size-fits-all, this is the product we inventory and try to put it in someplace else, then you run into problems.
Are there any guidelines as to how much of an intersection needs to be lit? If, like in our community, some of the intersections are lit, but recently some of the fixtures were replaced with LED add-ons, and you can see the LEDs now. I think they do project down below the original fixtures. You can see them quite far from when you approach the intersection. So it appears to me that there's no reason to light much farther, but I don't know what the guidelines might be.
It's what the community wants. There's really there's not a cut and dried standard.
What our community wants is not to be sued.
Yeah, well, the
And so
liability
they look
issue.
for something on paper.
Your
that
community
says-
has sovereign immunity if it's a U.S. jurisdiction, and so this notion that we must light or else we'll get sued is not a legally defensible position. But
That is not
you will
what
hear
our-
that commonly. They'll say, "Oh, well, we
Sure.
must do this."
That-
We
that's
have
not
to,
what
we
our
have to meet
town
the
lawyer-
standard.
That's not what our town lawyer told our town council.
Yeah.
Interesting.
Oh, yes, we hear that, but we'll hear also our insurance company mandates this. Really, which company is that? And
Yes.
you find out it's not that way at all. Yeah, you just hear rumor and hearsay.
Is glare a defined term, or is it just light that's not being used? Can you give me a...
Glare is a conundrum in the lighting industry. It's something that is still, there's no suitable metric for it, even after a century of trying to come up with something that's valuable. Because glare also has to do with the background. If you have a source, say a headlight, in the middle of the day, is not all that glaring. Okay, but if you take that same source at night and there's no other light around, it can be tremendously glaring. So what is glare? Is it the contrast ratio between what is bright and what is not? It's too hard to define
So
for a
glare is
specific object.
Glare is not necessarily something that's coming from, defined as something that's coming from the luminaire. It's something that's perceived.
Very
the other
much
end.
so. Glare is a
Is that
perception, and that's one of the problems for it. And they have different. They try to define different types of glare.
So one luminaire might glare to one person, but not to another?
Very much so. Okay. This is just sort of I'd say it's a caricature of actual color temperature. The correlated color temperature of a light, it's on the Kelvin scale. You can talk about black body if you want to. But as I see this, we've all kind of seen lights are available to the homeowner. And a 3,000 Kelvin lamp doesn't look like that to me.
No way.
Yeah, to me it kind of looks like this, and this is the 4100. But that's just the idea that, explain the black body.
It
Yeah.
exaggerates the intensity of the colors, but the point of the figure is these all represent themselves as being white lights. And that you get more or less of the redder colors or the blue colors depending on the design parameters of the light. And there's this number that's called the correlated color temperature that's supposed to indicate that to you. So generally speaking, but not 100% of the time, if that's a low number, it's going to have more of a warmer, redder glow to it. As those numbers get bigger and bigger, there's less of that red light. It's not a warm glow anymore. The words that I hear described as we go up the scale are harsh or hospital lighting or the mothership has landed.
Arc welder.
Arc welder. And this is at the core of what we have been pushing for a number of years now is for white lighting to make sure that you're below or at this number and you don't exceed it. Because virtually all of these lights that have higher values of this parameter really emit an awful lot of blue light into the environment, and that's the most hazardous kind of light really that we know of. Jen?
John, could you take a second and talk about the Photopic curve and the impression of color at different brightness levels?
You have the 1931 graph on here.
I thought that was a little too much into the details.
If you take a soft white standard incandescent light bulb out in the daytime on a bright day, it will look like that. It will look yellow in the daytime, but of course, in a lower ambient illumination environment, it'll seem much more white. So our impression of color changes
Yes.
based on the color level, and that's an important factor when we're talking about sports lighting or wayfinding lighting, is that there's no one magic number that appears white.
Yes, and the other shortcoming of this way of describing color is that unless it's what we call a thermal light source, so think about heating up a lump of metal or something, or the burners on an electric stove, first they don't emit any light at all, and then they glow red, and then they glow orange, and then eventually if you kept heating it, they would glow white. That's a good way of representing the spectrum of something like that, but if it's a non-thermal source, like most kinds of outdoor lighting, it is not good at all. And this is something that in the long run we would like to move away from this, because in some cases, especially for certain varieties of LED, it's really a terrible way of describing the spectrum of one of these lights. But for now, this is what everybody uses. You're going to encounter it out there in the wild, and just knowing that it has something to do with there being more or less blue or red light in a general way of speaking is what's important to know at this level. I agree.
So this is what a lighting engineer would be used to something like this, and I'm assuming. And then now it looks like 3000K is way on the other end. I would like to, this drives me crazy because 3000K now is not good enough, because we know we have better alternatives. And I sure would like to see divided 3 up at the top, and then go 27, 22, 1800.
Yeah, we can make different versions of this kind of figure. The point was to use one with the colors exaggerated, so you can really tell the difference between the steps.
Where do we start when we say high intensity blue?
Okay, well, this is where we come into another problem in the industry, is there's no standardization of terms. You'll see neutral white, neutral warm, warm neutral, warm, what the hell does it mean?
Cool white, cold white.
Yeah, and it's whatever the manufacturer term they want to point out, because there's not a standardization. So
But I mean, when we look at the impacts, or, looking at your devices and all, it's all that high intensity blue light, and I'm wondering what level is that?
Well, that's the magic things that they're trying to come up with, is intensity, wavelength, and duration of exposure. Is to quantify what is good, what is bad, because that's the magic 3. You can also add another metric, and that's the timing of the day is when you have that exposure. So it would be a 4th dimension. But exactly how much, how bright, what spectrum, what duration of exposure, what time of day, those are the magic numbers that aren't known.
Because I'm just thinking, you go to UV, you're just beyond the high intensity blue, and I recently bought a little UV flashlight, before
Look for
we started to look
scorpions.
for scorpions, as it was cloudy. And before doing that, before leaving for the start party, I went around the house looking at the glass that I collect to see if I would see any kind of really cool. And I did that for about 5 minutes, and 15 minutes later, I start seeing auras, and I had a 12-hour migraine, and I hadn't had a migraine headache for 30 years. Intense migraine. I had to cancel my plans for the evening, and I had to just sleep it off. And I thought, wow, am I a canary in the coal mine? Like, looking at that UV light, which is a higher, just beyond the blue rich, created a migraine in my brain. Because so.
Yeah, I mean, it could be, but you're our N of 1. I don't know if that's true of everybody, but it seems like there'd be enough people out there that they can certainly be tested. Yeah.
So this is a separate concept from how bright or how intense the light is, because you can have a very intense, more red light and a very dim, more blue light, and vice versa. So you have to, like Pete's saying, it's not just how intense that light is, it's also the color, it's how much exposure you get to it, et cetera, in terms of what effect it has on people.
Yeah, a couple of comments. As far as color temperature and being able to look at a lamp in the grocery or the big box store or whatever, we've had a requirement to have the color temperature on the box for quite a long time. So that's, double check that when you're looking at. We may not have the same criteria or requirement for commercial kind of things. Something I've observed as far as color temperature again, as a result of compact fluorescence, we have all developed a normal ingrained high color temperature acceptance in our brain, and it's something that we kind of have to overcome in our discussions with city engineers or whatever, that this bright part of the spectrum is good, but and I say that, well, we've gotten used to that, so it appears not to be so bad.
Well, and I could add to that, there's also I don't know if it's cultural, but there's certainly a regional bias towards the colder, whiter, bluer light. I attended a lighting show in Frankfurt. I was trying to get international involvement. And from about Turkey to Japan, they hate warm LEDs. Okay? They want 4,000, 5,000, that's it. Don't even think about a 3,000 Kelvin light in India. Okay, or Japan, or China. And I didn't really think about it. I went to Beijing and saw a bunch of 4,100 Kelvin lights in 2007. And man, it hit home when I went to Frankfurt and saw companies who wouldn't even think of going warmer than 5,000 because that's what their clients wanted in Taiwan. And it's a curious thing.
There's some places in East Asia where exposure to really bluish light is related to Eastern medicine, is believed to have positive health effects. And so you will see it in both in indoor and outdoor spaces. So it's culture dependent.
They may like it because they think it's healthy. Then is it more important that we do a public outreach to teach, let them know about the health issues of the blue light?
Certainly.
Yeah, we're up against a lot of tradition.
Yes.
That's the only downside. Okay, let's keep it moving as much as we can.
We talked about the notion of uniformity ratios. It has to do with how bright and dim a section of lighting goes. You can have uniformity ratios of 10 to 1, 20 to 1, 8 to 1. In some cases like this, it's like 1.5 to 1. The idea that is in what situation can you see an object better? I see objects better in low uniformity because I see it by positive contrast and negative contrast. If something is in front, sitting here, I see it as a background for the light back there. If it's in here, I see it illuminated. So you can see something by both positive and negative contrast. If you have an object in here, it's washed out. You don't see shadows. I don't see contour. I don't see texture to it. So the idea that uniform is preferred, it's subjective too. I certainly don't find the uniformity to be a very good thing. At night, I see by contrast whether positive or negative. And lighting designs will take this into consideration. It seems as you get into more urban, high traffic or high pedestrian areas, the uniformities are designed to be more uniform. If it's strictly for automobile traffic, the low uniformity still has its place in design.
I'm going to step through these fairly quickly and not dwell on them too much, but you will often hear about different kinds of lamps, and having just some idea of what these are relative to each other is kind of useful. So I have a couple slides that show this, and so in each case you have the name of the type of the lamp, a picture showing an example of it to remind you where you've seen these sort of out there in the world. And then next to that is a spectrum that shows the distribution of light as a function of its color for each of these kinds of technology. And the main thing that you'll notice is there's lots of different ways to create light, whether it's white or another color, but most of these are trying to do something that looks like more or less like white light. This is what I was talking about, a thermal light source. It has a spectrum kind of like the sun, just a really hot object. It sort of emits light of all colors. These are decidedly not thermal sources because they don't look at all like that. There's a little bit of light here in the blue, and then there's nothing, and there's a little faint light in blue, and then there's nothing, and then there's green. And you can put these together in lots of different ways that will give you lots of different results. And the color of that light, and then of course the type of technology that's involved in creating it goes into the lighting design. So the only point of showing this to you is knowing that there are lots of different ways to do this. The world is increasingly going towards one of these types in preference to all the others, and actually its spectrum is part of the reason that we are so worried about it. So I'm not going to go into a great deal of detail about any of these particular lamp types. Just know that there's more than one out there, and they have these different kinds of characteristics. And then there's the matter of controls.
This is one of the areas where LEDs hold both promise and peril. This is part of the promise, is the ability to control it. The previous technology, commercial-wise, where you had these arc tubes that struck and took a while to get bright and dim, you couldn't have the notion of dimming or curfewing dim hours or sensing if something is occupancy presence to ramp back up. The old technology simply didn't allow that. The new technology of LEDs does. So the old technology also was kind of how all the laws and standards and regulations were formulated. They were formulated upon a technology that didn't have capabilities that the new stuff does. So we're just now getting into standards and recommended practices that will actually take into account dimming, that it can be done. It's a sanctioned thing. We're not turning the light off, we're dimming it, which is counter to what people normally thought of with lighting. There's something else that's missing on this. Timer's important, dimming, photocell is important. Right here should be motion sensor. Okay, because that's a really critical thing, particularly with security situations. A steady state light in a security situation is not more secure than a light that suddenly pops on. People become accustomed to a light that's just, yeah, it's there. And if it was at a school and you saw somebody walking by, it's a janitor or whatever, you don't know. But if it's normally dark and suddenly the light pops on, everybody looks. And it's that which is what makes a security situation better. Because people, you got eyes on it now. And we're so knowing something's different. I need to check that out. And most perpetrators don't hang around to see if it's a switch or a dude. Checking to see what it is. Sir?
I just want to quickly comment on this. I was talking to a gal in our, I think, local chapter, but she was saying, in a residential zone, for example, do you have people looking out and seeing what's going on outside for public safety, or do you want everyone shutting their curtains because the light is so bright and no one can see what's going on?
Well, the light doesn't have to be so bright. I mean,
Well, I'm just saying,
That's what's happening.
that's a
Yes.
flip on the public perception of
Yes.
public safety.
Yeah,
Yeah,
yeah.
so.
It is, and it's, yeah, perception's everything. Because you'll go to another neighborhood and they won't do that at all because they have, it's in their mindset that, you know, if it's even lighting and everybody's, you know, being a good neighbor and watching out for everybody, that's a safer situation instead of, you know, the prison yard effect. Yeah.
So controls are a good way to help achieve that I showed you earlier that we call the 4 Ps, about the proper time and place and everything. This helps us adapt the lighting to the conditions where it's needed, and then helps us turn it off when it's not. And things like LED have actually helped because now instead of the old street lighting systems in particular, you had to wait. If you turned off one of those sodium lamps, for example, and you tried to turn it back on, it would be minutes before it would come back on because of the nature of the technology. Now that's instantaneous. And we can dim them in a way that we didn't used to be able to do. So this enables us to do things with design that we couldn't do in the past. Okay, I'm going to have to abbreviate some of this because we have about 25 minutes left. I do want to say something about LED lighting because it's sort of the biggest challenge that's in front of us right now. Our history of lighting started with burning carbon of various forms in oil lamps, and now we're using solid state technology that actually has to do with quantum physics to produce light, and we've tried everything in between. But I'm going to argue that LED is different. It's different than all of these other past types of lighting technologies that we've had. Very, very briefly how it works. Underneath every white LED, there's a blue LED. And we use a material called a phosphor to make all the other colors. So the blue LED shines blue light onto this phosphor material. So the blue light is underneath this, that's that blue curve. And then through a process called fluorescence, we convert some of that blue light into other colors, namely, once again, red and green, because that's what we need to see colors with. And the overall result,
The parent LED is done. That's Shuji Nakamura's, you know, his Nobel Prize. Now everything slopped on top is where the magic happens. And talk about the color shift, they're referring to it as phosphor fatigue. Okay, and it's not getting the right, you're seeing some spectral shifts. I'm seeing some of the early gas station models are now having distinct green hue to them. And they started off white 8 years ago. So
8 years.
8 years. We're seeing that kind of shift. And that was the, you know, the early age, the early adopters 8 years ago in LED technologies, pre-Cambrian, okay? But it's moving so fast. So the magic in the phosphors is really
But they don't
the key.
do things like put filters on the outside of the light or anything like that.
you can, but generally not. But you can, this is a material where you can change the chemical composition and you can get almost any desired effect out on the other side. But you're right, the more of this blue light gets converted to the longer wavelengths, it runs a little bit less efficient in terms of energy. So there are some losses in here, namely to heat. And so the push to these real high efficiencies has been about trying to make this the process that results in the least amount of conversion. Yeah. So they're good, go ahead.
Yeah, we had a question last night when we were looking at an example of amber LED lighting and the problem of it being inefficient, and we didn't really know the percentage of how inefficient it was. There was 50% or 90%.
The efficacy that you're getting out of a true amber chip, not a phosphor converted amber, is like 30 to 40 lumens per watt, whereas a good 3,000 Kelvin LED will get 150 to 160 lumens per watt. So there's a tremendous penalty going with a chip amber-based product. Phosphor converted, where you're actually using just a tremendous amount of different phosphors to eliminate that blue, you're still going to get a, the shoulders are broader on here at that 590 line for the amber. So there's still going to be some slop, to the point where Florida Wildlife Commission will not sanction PC amber chips for turtle lighting because there's enough below 560 nanometers to say that they're not good. So they only allow the chip amber. And there's an efficacy penalty with it, no question about it. Yeah.
But what's the lumens per watt of a traditional incandescent bulb? I mean, if we're talking about
15? Yeah, oh,
Right,
it's
so
twice as good as an amber. I know, but when you got jurisdictions and utilities talking about saving with LEDs, they're, you know,
so
10,
regardless
15
of
times
what
the
LED
savings.
you choose, you're going to save a lot of energy over using the older
Over-
technology.
Over an incandescent, yes,
Yeah.
right. But, you know, is twice as good enough?
Well, it's 10 times as good as 5 times as good.
Yeah.
That's where I've come down.
I know. There are other,
They're gonna save a lot of money either way. And
will they use the phosphor converted, or will they use just the chip amber? I know there's plenty of people looking for chip amber that is, has greater efficacy.
right.
Will it happen? We'll find out.
So are the lights like the Tucson City used, are those phosphor converted LEDs still? Okay.
So there are good things and bad things about this way of generating light. One of them is that, that's good, is that we have extreme control over where that light goes. LEDs are very highly directional light sources, which means the light that's coming out of the end of that little capsule that I showed you in the last picture likes to travel in parallel lines to its destination and doesn't get really scattered outside of that. So the result is moving from this lighting installation on a sports field to this one. Now you don't see those sources of light on the poles so much anymore. There's a little incidental reflection, but not very much, because that light is really aimed right down onto the field. And then instead of irregularly illuminating that surface, it's very even, and it comes up to the edge of the track in this case, and it basically stops. We really can't do that with older types of lighting technology, so this is an aspect that's good. And another that's good, because you can control what's in that phosphor material, that the resulting spectrum that comes out the other side, you have a lot of control over that. This is a thing we call a spectral power distribution. You don't need to know those words. We call it an SPD. Think of it as a rainbow. The way the light is distributed across the different colors depends on the type of technology, and we go from natural sources of light to progressively more unnatural sources of light. And how the shape of that looks like is highly dependent on what you put into that phosphor material. And you can do a lot of very good things about that. The downside is, as my colleague here likes to say, is that you also run into the possibility of playing God. Because you can say, oh great, well we know sea turtles have a problem with blue light, so let's create a kind of a light, a mixture and a phosphor that gives us light that's good for turtles. But then you have some species of migratory bird that's highly attracted to that orange light, and you have just shifted the disadvantage from one species onto another. So you have to be really mindful about what are you lighting for, whose benefit is it, in order to determine how do you want the shape of this spectrum to be. But this is something that we really couldn't do with older technologies. We were mostly stuck with what we had from those different types of lighting. So here's the challenge. The challenge is LED is changing the way our cities are lit, and it's changing the color of the cities. It has its own set of problems that are associated with that. A lot of times they're worse on glare. They're emitting a lot of this blue light to the environment that we've suggested is harmful. As I said, they're changing the color of our cities. This is two views of Milan in Italy, before and after they changed the lighting in their downtown area from mostly sodium to mostly LED, and the astronauts could see the color change from orbit. It also has the potential to make sky glow over cities worse if it's not handled correctly. The converse of that is also true with a really well-designed LED system that's good and shielded and the light levels are appropriate, and you're trying to avoid emitting blue light, you can end up with a better result. This is an example of what happens in simulations. If you have a city that's mostly low-pressure sodium light and you convert that light to white LED, and you don't do anything about the quantity of light that's being emitted. So the quantity of light is exactly the same in both these cases, but because blue light scatters more strongly in the atmosphere than other colors, which is why the sky is blue during the daytime, the result is that the sky glow over the city would get worse, and that's what we've been warning people against. As a tiny self-promotion moment for my poster this afternoon, I'll be telling you how you can actually reduce sky glow if you do your design correctly with LED. So this doesn't have